Hi, and welcome back to the Role Model series, where we sit down with the people who have shaped astrophysics and hear the stories behind the science. Today, I'm thrilled to be joined by Dr. Sarbani Basu, one of the world's leading solar physicists and a pioneer of modern helioseismology. From Chennai to TIFR, from London to Princeton to Yale, her career has helped redefine how we understand the sun's interiors. I'm so excited to share this conversation with you. Let's get started. You studied physics at Women's Christian College in Chennai, and then Pune, and then you completed your PhD research at Tata Institute of Fundamental Research.
Yeah,
When you look
that's right.
back to that period in India, what first drew you towards the sun and not black holes or cosmology? Was it a specific class or a mentor that led to this interest?
It was a fairly different route. In India at that time, the only way you could do astronomy is by studying physics, which is actually a good thing, which is why my bachelor's and master's are in physics. But that when I was doing my PhD, my topic actually was what at that time was called galactic chemical evolution. These days, it's sort of a part of what's known as galactic archaeology, which is the study of how our galaxy was formed, how the different constituents came together, how did the chemical abundance increase. Now, in those days, and I'm talking about the very late 80s and very early 90s, the data were really vast. So all the models I made fit the data, which was very, very frustrating. Also, I couldn't see a path forward. And that's the time when helioseismology as a discipline, which is the study of solar pulsations to figure out what is going on inside the sun, that was just coming up. A few groups in the world, but then at TIFR Mumbai, it was of course Bombay those days, there were two faculty members who were solar physicists, but were beginning to get into the field. Now, in those days, the PhD degree was given by the university, not by TIFR itself. It is given by TIFR now. And there used to be a long wait for the thesis to be evaluated. So while I was waiting for the thesis to be evaluated, I asked these two faculty members, Professor S.N. Chitre, who unfortunately passed away years ago, and Professor H. Antia, whether I could join their efforts. I did. And thanks to Professor Chitre's network, I managed to get a limited time postdoc in London and then got a proper postdoc in Denmark. So I spent 3 years in Denmark, which sort of established me in my field. And it was then when Professor John McCall from the Institute of Advanced Study in Princeton asked me if I would like to join him in Princeton. This is not the university. This is a small private institute within Princeton. It's basically known for the fact that Einstein worked there and people like von Neumann worked there. So that's how I ended up in Princeton. I did get a job offer in India, but I'm still talking about late 1990s. India still didn't have too many opportunities. So John Bacall basically persuaded me to apply to Yale because Yale had advertised a job. And I got the job. Here I am today.
That's a very interesting pathway to have sort of the interest originated initially during your thesis period and that continued. Oh,
So that's the interesting thing because the Kepler mission, which was launched in 2009 as a planet search mission, also provided seismic data on other stars. So that is when I started also in astroseismology. Astroseismology is very precise ages of stars, which sort of feeds into this whole galactic chemical evolution study. So, in some sense, it's almost a full circle. Because astroseismology, the study of, of stellar pulsations, feeds into now studies of chemical evolution of the galaxy. So I've even been involved in a few papers. So I don't do it full time. So in that sense, it's come full circle. I must say my path was helped by the fact that I did work very hard, but I also had very good, and it turned out I was in the right place at the right time, which matters because yes, you have to work hard, but unfortunately, sometimes luck matters. And I consider myself very lucky.
You do raise a very important point of how luck influences your journey so much.
Exactly, luck matter. Yes, nothing substitutes for hard work. Because when I was postdoc trying to establish myself in this field, I used to do what is considered very unpopular these days. I would work 10, 11 hours a day and even put in hours on the weekend because there was no way I could establish myself in a brand new field and get a job unless I did the work. So I was willing to do the work, but the fact is I was there because my mentors helped me. And as I said, this was the time when helioseismology as a discipline was taking off.
I think it's really beautiful the way you shared how it comes back to the starting days of how your research does lead to a full circle. Because there's a combination of hard work and luck. And I'm interested how you mentioned your journey from going after your PhD to London and then Denmark and then coming to the United States to Princeton and then Yale finally. What do you think was sort of the hardest part from transitioning from India's academic environment, something you had been used to for so many years, and then moving to these international labs at that time?
London wasn't very different. But then we borrowed so many things from the British, or rather, when the Brits were in India, we just kept some of the stuff. So London actually was not very different. In terms of academic climate, too, it really wasn't very different. But the thing is, TIFR is not like Indian universities. The atmosphere there wasn't that formalized and all of that. So, I mean, it was much more because we had a lot of international guests all the time. So TIFR was different from Indian universities. So when I went to TIFR, that was different. But Denmark was more because I didn't speak the language. Almost everybody spoke English. That was a problem. That when people tended to gather together, they'd often switch into Danish, which was a bit of an issue. Denmark is otherwise a lovely place to, except the winters are very dark. So biggest culture shock, though, was going from Denmark to Princeton. It wasn't how research was conducted, it was just daily life. So when I moved to the US, I know how to drive. Of course, I didn't have a car because I didn't know how to drive. And even something as simple as getting a social security number, you had to go to another town because Princeton didn't have a social security office. While in Denmark, the Scandinavians very gloomy, grumpy, but they are very helpful. While in the US, everybody's, hi, how are you? But you have to do everything yourself.
That can be shown by how helpful people were when you initially came. Transitioning from your initial days to the work you do now, you've often mentioned how, in a way, working on the solar neutrino problem was sort of the significant aspect of your career and something you often recall repeatedly. And how you showed that the solar neutrino problem wasn't a failure of solar models. So, could you just briefly explain the work and share if you remember anything about the first time that conclusion became clear?
Let me go back to what the solar neutrino problem is, or rather was, because it's one of the few problems in astronomy that has been solved completely. It's now for the physicists to worry about. So, the byproduct of nuclear reactions are these particles called neutrinos. Until the mid 60s, the fact that there are nuclear reactions in the stars were more of a theoretical understanding. So the question is, how do you prove it? So that is when Ray Davis Jr. he came up with the idea, why don't we try to observe solar neutrinos? It's very difficult to observe neutrinos because neutrinos just pass through matter. At any given time, there are millions of neutrinos passing through you. But anyway, they made a neutrino detector to observe solar neutrinos. And to the surprise, they found that the observed number of solar neutrinos was about a third of what is predicted. So that was the beginning of the so-called solar neutrino problem. Now, stellar models are complex. It requires a lot of physics inputs like, nuclear reaction rates, equation of state, mixing processes. So, of course, the first thought was we're not making the models correctly. This is where helioseismology comes in. Because with helioseismology, we can figure out what the structure of the sun is without reference to models. And basically, the structure of the sun was very, very, very similar to our models. In other words, our models were actually pretty good. So what was happening? So about the same time, the original neutrino experiment was going on, and people built other neutrino experiments with different detectors. So in Japan, there were so-called Kamiokande and Super Kamiokande detectors, which were based on water. And in Italy, there were gallium-based detectors. Now, it turns out they all gave the same thing, that the number of neutrinos detected was less than predicted. But the detector detected neutrinos at of different energy ranges. You couldn't really reconcile the measurements from chlorine, which was the original experiment, the chlorine detector, the water detector, and the gallium detectors. So that was the so-called less known second neutrino problem. Now, this is when people like John they had the idea that our models are correct. So what's going on? At that time, the model of the neutrino was that an electron type neutrino will remain an electron type neutrino, a muon type neutrino will remain a muon type neutrino. However, if the neutrinos have mass, one can change to the other. And it was also shown, it's called the MSW effect. They showed that in the presence of matter, this conversion would be phylistic. So that is when we came up with the idea by we, I mean, it was mainly John who was the theoretical proponent, that what's actually happening is that neutrinos have masses. So the models are fine, but of course, particle physicists like to have their own proof. That is when the Sudbury Neutrino Observatory was built. Uses heavy water as a detector, and that detector can not only detect electron-type neutrinos, which are the majority, but also muon-type neutrinos. And once the detector started taking observations, there was no neutrino problem. The number of recorded neutrinos, which was a combination of electron-type and muon-type neutrinos, was exactly as was predicted by the models. So that was the end of that problem. That's There are very few problems in astronomy where you can put a underline and say, okay, done, let's go and do something else.
I mean, it's so fascinating to hear. I mean, especially how you point out that there are so few problems that have been, as you said, completely solved.
Yes. Once we showed it's not an astronomy problem, because yes, I mean, our solar models are not perfect,
Yeah.
but they're good enough that it wasn't the cause of the neutrino problem. There are other issues with solar models, but that's fine. We are waiting to solve them.
If I remember correctly, this is what led to a Nobel Prize in Physics.
Yeah, so Ray Davis and the director of the Sudbury Neutrino Observatory, they got the Nobel Prize. And most of us thought the third should have been John Bacall, but yeah, he didn't get it, unfortunately.
Often you've talked a lot about your research and your studies, and I want to know beyond just the work you do. You have mentored students from India, the US, Europe, various parts of the world. And is there a moment with any student where maybe they've struggled, like maybe once you did, and that changed the way you mentor students?
Every student is unique. And so I've had to change my mentoring style to suit them. Some students, you just tell them, give them a hint of a problem, they'll go solve it and suggest the way forward. Some people, you give them a problem, they'll be able to solve it, but not be able to come up with the next question. So you have to give it to them. While with some, you have to keep holding their hands. So it completely depends on the student. I mean, the first type of student who can just take off, they're the ones who will be really successful as researchers. Because by the time they finish their PhD, their colleagues are no longer your students. You're
Yeah.
collaborating with them. You're no longer supervising them.
Yeah, I think that's an important part of mentorship, as I understand that you can't have one style for mentoring someone. You adapt it to the student you have.
It has to be. Otherwise, I mean, it won't work.
Right. And how do you think, or when you mentored certain students, they've transitioned from the initial hand-holding to being, as you said, colleagues or being collaborators in the work. How do you help them transition?
Because you have to refrain from telling them, oh, try to solve it this way and that way and hope they come up with. If they can come up with the solution themselves, they've already made the first step. The next step is asking them which direction the research should go and giving them the space to do.
I think those are important sort of pointers for anyone to keep in mind when they mentor someone and helping sort of guide students into pathways that allows them to succeed.
And this is where I've seen mentoring styles differ in a lot of places. I don't know what it is in India today, but when I was a student, the mentor was Guruji, basically. Questioning was not encouraged, put it that way. I don't know what it is today. I mean, I left India in '93, and I haven't really worked in any Indian institution since I left.
Like it's slowly evolving into a culture where you can work, sometimes against your supervisor and have your own opinions, which I know initially wasn't the way it is now.
Yeah, because India's had this old tradition of guru being right. I mean, we have these tales about to cut off his thumb for his guru. I mean, I blame the guru. What sort of guru is that? I mean, you're favoring one student over the other.
Yeah, I think a lot of Indian mythological stories have instances like that. And I believe that's what led to the culture the way it is. But
Yeah, yeah, it is. So, yeah, we are an old civilization, so we carry that baggage, and the question is, it takes time.
definitely. So I always wonder how you've led graduate admissions and influenced, in a way, solar physics strategy through various committees that you have chaired.
Mhm.
Was there ever a point where these responsibilities affected or pulled you away from doing science?
Absolutely. You can't, like, when I was there, I could barely do any science. And that's a known thing,
Okay.
which is why, at least at Yale, the chair's position is a rotating one. And it's not just at Yale, it's everywhere else. Like, I have a good collaborator in England. I used to go to England every summer till 2019. 2020, of course, COVID intervened and my trip was cancelled. And I didn't go after that because the person I was collaborating with became the head of his department and had no time. So he stepped down this year. So I went and worked with him, preparing, writing up stuff. And so that's everywhere. Yes, it does. At some point, you have to give back to the community. And this is how we give back to our community. Like setting policy. Yes, set the policy so that the people who come after you, and if you're lucky, even while you're still working, will have better resources, have a better direction.
I think even while you have to sacrifice your scientific rigor or being able to work as a researcher while you enter into these roles, I think you highlight how giving back to your community is very essential, knowing that it's the same community that has given you so much for so long.
Yeah, because if you don't do it, who will? It is the people who have gained some seniority, who have a track record which others will respect. Yeah, if they say something, at least there's a chance that they'll be heard.
So many young scientists like me look up to you. Can you share Can you share a moment in your early career when you had self doubt or you felt underestimated, like a lot of young women do? And
Yeah, the imposter syndrome is, of course, a big problem. And India in the late 80s, early 90s was not very hospitable to women who were good. And if I hadn't changed my field, I might have dropped out
so,
because I had wanted to do astronomy ever since I was a child. I had a fantastic science teacher in my third and fourth standard. And she's the one who inspired me, to talk about planets and all the missions that were being prepared to go to the planets. And that's when I got the astronomy bug. But as I grew older, I kept that, but I also had a sort of a fallback ambition, if you could call it, because if after my PhD, this wouldn't have worked out, I was going to appear for the civil service exams in India. I was always pretty good at these general knowledge things. I was always interested in what was going on everywhere, and that was going to be my fallback. But yeah, doubts are normal. And imposter syndrome is normal. If you're any good, you'll have imposter syndrome. It's people who are not good who think they're fantastic.
And what advice would you give to people who deal with imposter syndrome, especially who do feel the need to quit because they don't feel they deserve a place in science? How can they push for?
My advice would be go back and look again at your own record and see what you have done. Don't believe the feedback from one person just because one person has given you a negative feedback doesn't mean you're not good enough. That is why also one should always cultivate multiple mentors, not just your supervisor. Your supervisor can't support you in every way. And besides, I mean, if you're doing a PhD and you want a postdoc, you need at least 3 letters. So always have multiple mentors. Seek them out for advice on different aspects. So,
I think
because my relationship with my supervisor was quite rocky, but the other mentors, like the people who helped me go from galactic chemical evolution to uh, helioseismology, I've had a series of really good mentors.
are there any specific mentors that you think really inspired you and guided you that you would like to share?
So I would say 4 or 5 people who I look up to. It started with Professor Chitre and Professor Antiga. So Professor Chitre unfortunately passed away, and my next mentor in England, Professor Ian Roxburgh, he helped me because he basically gave me a job even when I did not have a track record in helioseismology. So I'm forever grateful to him for that, because without that, again, I wouldn't be here. And he was one of these hands-off people, but very practical. You should do this, try and do that. And then when I went to Denmark, Professor Jan Christensen Lundowski won the Kavli Prize a few years ago. He treated me like a colleague, even though he was my supervisor. And then, of course, John Bacall was another person. I mean, I was his colleague, basically. He helped me navigate the US academic system.
I think it's beautiful to hear the role the mentors have played in your journey, and especially how mentors believed in you when at times you didn't believe in yourself. And I think for students, it really highlights the role of choosing good mentors and sticking with mentors who inspire you.
Yeah, you have to look around. As I said, I was lucky, and except for my supervisor, with whom, as I said, I had a rocky relationship, which is nothing surprising. Many people have rocky relationships with their supervisors. But the later people I worked with turned out to be fantastic. And then, of course, like when I came to Yale, of course, I was a professor, but I didn't have any formal supervisors or mentors or bosses. But the 2 people at Yale who helped me navigate the Yale system, one is Professor Pierre Demarque, and the other basically taught me the Yale system, because every university has its own quirks, and the other was Professor Sabatino Sophia. He's retired, and he was another influence who basically showed me how to work in collaborations, because he always had worked with collaborators rather than solo. Professor Demarque, Pierre was more solo work, but Sabatino always worked in collaborations.
I think those are very key lessons that you share that you've learned with your mentors. And I think some important lessons that I feel the viewers should know about. How you've spoken a lot about the importance of patience in solar science, how, let's say, solar cycles take decades for those patterns to be observed.
Yeah. I want another 10 years of data. I have a hypothesis about a change, but I can't prove it without another 10 years of data. I hope I'm healthy enough to keep working for the next 10 years, and B, the missions which provide me data keep working, because nothing is guaranteed.
And let's say for a student entering this field today,
Mhm.
used to fast moving results and quick papers, what mindset do they need to cultivate to stay in love with long horizon science like solar physics?
You always have to do short horizon science. So, like in 2009, when Kepler went, I almost completely shifted my focus to stellar astrophysics and let the solar data keep getting accumulated. But now, the last couple of years, we have a lot more data, so I'm back to solar. So you have to be nimble, look at problems which you can solve, but see the fast moving frontiers are. And some frontiers, because of data limitations, are not fast moving. For example, the sun has a 10-year cycle, nothing we can do about it. You just have to be patient. But which is why I've come back now. Now we have 30 years of data. So I'm back to it. But for a long time, nearly, I would say from 2009 to 2018, 2019, I was just doing stellar astrophysics.
I think now I realize how important that is to learn and do, because you do need to remain, in a way, in the science and pick problems that allows you to work even more.
Yes, similar problems that are similar enough so that you already have the technical expertise. I mean, yes, sometimes you are forced to learn new techniques, et cetera, and keep up to date. But I wasn't suddenly going to shift from studying the sun to studying black holes. That's a completely different discipline.
You say astroseismology is just given a different label because collecting that data is harder than collecting the data from the sun. How exactly do sort of the difficulty in data collection differ among, let's say, collecting seismology data from other stars compared to a sun?
Before Kepler, the only astroseismology data we had was A, ground-based, B, it was from observing changes in stellar spectra, which actually gives you better data, but then from the ground, you have the day-night cycle. You're not going to be given too much time on large telescopes to have a long time series. So we had very little data, but Kepler changed things because Kepler looked at the change of the brightness of stars. You can't do that from the ground because the atmosphere intervenes. Kepler went above the atmosphere, so it could detect changes which were parts per million, okay, in the brightness of a star. And Kepler observed continuous. So we have these long continuous data sets. Yes, Kepler was looking for relatively large changes in the brightness caused by a planet coming in front of the star. But it's the same data that we use, except we don't look for the transits. We just look for the continuous changes. So Kepler changed the game. TESS is continuing. Yes, because the pixel size are much bigger. It doesn't observe that long any particular field. Is much more challenging to do seismology. So I'm looking forward to Plato, which is the European mission, which is supposed to be launched in December 26th. It's still going to be staring at one part of the sky for a while before it skips to another part of the sky. So that will give a lot of data. And then one of my colleagues, Amelia, is proposing another seismology mission called Haydn, which is to look specifically at stellar clusters.
It's interesting to hear how much has evolved since Kepler sort of laid the foundation, and how much sort of information we can gain from just looking at the continuous series that we get from test data and learning so much about the interiors of those stars through that data. I think that's incredibly fascinating. But I've the last question to ask you now. It's a question I ask every person I interview. What do you think is the best part of being an astrophysicist, of being a scientist?
The research is fun. You're answering some questions which cannot be answered on Earth. like the neutrino problem. I mean, if you're more philosophically inclined, then of course study cosmology and try to look at the origins. And the other thing which I often tease people about is that if I make an error, nobody dies. Not like a doctor or an engineer, you know. I can do my research knowing fully well that hey, okay, I'm not going to harm anyone. So, I mean, that's a very avoidant thing to do, but not everybody can work things where you're comfortable taking somebody else's life in your hand. If you're the type of person who's afraid to be a doctor because you'll have to take life and death decisions, or you don't want to be a civil engineer because you're afraid the bridge you built will fall down, frankly, I would think doing research in astronomy is at par with, say, being a philosopher to affect lives, but only in a very broad sense.
That's very interesting to hear. And I think it's really nice to hear the way you sort of look at science and pursue science. And it's incredibly inspiring to hear, I mean, in your voice itself, the passion with which you talk about the work you do and sort of the lessons that have shaped your journey as a scientist. I know I took a lot from this conversation, and I really hope any student listening to this does do take the same from this conversation. Thanks for joining us. Dr. Sarbani's story shows us how far curiosity and persistence can take you. Thank you for watching, and I'll see you in the next episode.